Lithium batteries are used to an ever-increasing extent because of their excellent qualities, such as low weight, high energy content and slow loss of charge when not in use. They've become part of our daily lives through our use of consumer electronic articles like laptops, digital cameras and cell phones. The energy content in a rechargeable lithium battery is twice that of a nickel metal hydride battery. This means that your device can run for twice as long before it needs to be recharged. The high energy content makes this battery potentially dangerous. In the past, lithium batteries have caused explosive fires, destroying factories, warehouses and equipment where such batteries have been in use. However, battery safety has improved over the years. Despite an enormous increase in the use of these batteries, the frequency of accidents has dropped drastically. Still, incidents of laptops and mobile phones catching fire are not uncommon even today. Oil and gas industry operators, both on and offshore, such as Gasco and Statoil, use a great variety of equipment containing lithium batteries. These batteries are different from household batteries in one significant way, being much larger and containing much more energy. In 2002, 5 transponders were placed 374 metres below sea level on the Norn field on the Norwegian continental shelf. 2 years later, only 1 transponder was still functioning. It was therefore necessary to replace the dead batteries with new ones. The operators of the motor vessel Edda Fon suspected a high internal pressure in one of the transponders, and on opening the first half clamp which held the tubed housing and transducer together, they noticed that the 2 flanges were apart. The second half clamp was removed with extreme care. The content of the transponder was ejected at high speed and hit a bulkhead 3 metres away from the original location. A huge amount of smelly gas was liberated.
In April 1999, the Statoil PIG team prepared a 36-inch MFL inline inspection tool on board the Heimdal platform. The PIG consisted of a magnetizing, an electronics and a battery module.
The PIG was launched and then propelled by the product flow to the other end of the 150-kilometre long subsea pipeline, ending up at the Draupner platform. The PIG arrived.
Everything appeared normal. The pig trap was depressurized and we opened the pig trap door in order to pull off the pig. The magnetizing unit appeared, the electronics unit appeared, but then nothing. It was a total shock to realize that the third unit, the battery module, was lost.
The only evidence that a third module had ever been there were the twisted cables and the ruptured tow link. The module was definitely somewhere in the 150-kilometre long subsea pipeline. After 4 months of planning and testing, the battery module was retrieved. The module had obviously experienced devastating forces in the pipeline. Any clear reason for the disintegration of the battery module was not apparent. Together with the technical safety in-house unit, the PIG team decided to suspend further inline inspection operations until they could feel sure that they knew the reason for the incident.
Statoil's internal investigation of the incident concluded that the sequence of events had been as follows. The tow link ruptured, then a leak developed in the pressure-sealed battery module body. The leak caused the pressure build up inside the battery module, and finally the battery module disintegrated following an internal explosion.
Several studies were initiated in cooperation with the Statoil in-house unit for technical safety. The analyses pointed out a number of various risk elements and unfavourable operating conditions. However, the Pipeline Operations Department still needed help to single out the few remaining risk elements and try to eliminate or at least control them. In order to do so, it was essential to understand better both the failure mechanisms and the reactions.
Based on the reports and papers, the conclusion was clear. Let's get in touch with FFI.
In cooperation with Statoil, Gassco and Kongsberg Maritime, FFI, the Norwegian Defence Research Establishment, has conducted a series of controlled destructive experiments on lithium cells and batteries.
The Norwegian Army was among the first to introduce lithium batteries in the late 70s. This had to do with these batteries' excellent performance, especially at low temperatures. Of course, the Army had their share of explosions, and the Army Battery Laboratory burned down in 1980. After these incidents, FFI has been involved in safety-related work on lithium batteries.
At present, the FFI is actively working on lithium-ion batteries for use in autonomous underwater vehicles such as those of the Hugin family, and as a power source for future soldier systems, the Normans project.
The high energy content as well as the hazardous components make it very important to investigate the battery's response to abusive conditions. Conditions like a massive internal short circuit, the effect of increased external pressure, and of external heat caused by fire.
In order to provoke a massive internal short circuit, the battery group at the FFI performed several nail penetration tests. In the experimental setup, a heavy weight fell inside a vertical tube. The weight hit a nail, causing a rapid penetration of the cell. These tests used a double D lithium sulfuryl chloride cell. This was the same as that used in the in-line inspection tools. The sparks are burning lithium. The smoke is irritating, poisonous, and corrosive. It's clear that a fast and uncontrolled release of energy in a lithium battery can be devastating. Having seen the results from abusive tests on single cells, the battery group at the FFI decided to perform full-scale tests on real batteries. In the oil and gas industry, in-line inspection of pipelines is a frequent activity. Imagine that a battery is exposed to too high a pressure during an inspection. The cells collapse and become unstable. When the pig arrives, the battery explodes in the pig trap. The question then is whether the pig trap is robust enough to withstand such a blast. In 2006, the FFI conducted an experiment investigating the consequences of increasing the pressure beyond the collapse pressure of the sub-battery confined in a simulated pig trap. The battery used in the test contained 21 cells. The pig trap withstood the explosion. The total movement of the pipe section was measured to 80 millimeters. The pipe, including the end plates, weighed about 1,300 kilos. All 21 cells were found. Only 4 cells had exploded. From the recorded video, it's possible to make a crude velocity estimate for the different parts flying inside the pipe. As an example, the 35-kilo battery container achieved an average velocity of 133 kilometers an hour. The next experiment was conducted to investigate the effect of fire in the pig battery. 2 important questions had to be answered. Would every cell in the battery explode, and how dangerous would the situation be for firefighters? The battery container was placed in the centre of the experimental setup, surrounded by 3 aluminium screens. When it comes to penetration, the aluminium screens give the same quality of protection as the firefighters' protective suits would have done. After approximately 15 minutes of heating, the battery container exploded. As in the previous experiment, the smoke produced is irritating, poisonous and corrosive. In addition, there were a lot of fragments of different size and quality flying through the air, including burning lithium. The 35-kilo heavy empty container was found 24 meters away from the original site. The largest lid, weighing 16 kilos, was thrown 42 meters away. The battery container and the largest lid had penetrated the aluminium screens and left clear marks. Indents of cells could also be seen. In this case, only 4 of the 21 cells had exploded. The next test to be carried out by the battery group was to study how important the cell construction is when it comes to the degree of danger. 2 batteries of the same chemical content were heated up. Only one of them was constructed using cells with vent. A vent opens up when the internal pressure in the cell exceeds a certain limit, and this allows the electrolyte to evaporate. The batteries were placed in an elevated steel tube which was heated from the outside using a torch. Once again, aluminium screens were used and placed in the direction of possible ejection. First, the battery with vents was heated up. After 6.5 minutes, the cells started to vent. After 14 minutes of heating, the fire was extinguished by itself. There was no ejection. In the second case, the cells in the battery had no vents. After 10.5 minutes of heating, the battery exploded. When the ejection hit the screen, it reignited. In front of the fireball, you can see cells hitting the screen. Later, sparks of burning lithium are visible. When we keep in mind that the screen gives the same protection as a firefighter's suit, it's obvious that injuries could be serious. The benefit of vents is clear. If a lithium battery is burning, what should be used to extinguish the fire? According to some battery manufacturers, water should not be used to extinguish lithium battery fires. It's claimed that lithium reacts explosively with water to form hydrogen, and that the presence of minute amounts of water may ignite the material and the hydrogen gas. Based on experiments performed by the FFI, metallic lithium reacts slowly with water, and the reaction rate is so slow at moderate temperatures that it doesn't compromise safety. Some battery manufacturers recommend using a graphite-based extinguisher, alternatively a metal fire extinguisher Class D, which contains a mixture of inorganic salts. A Class D metal fire extinguisher is a part of Statoil's fire emergency equipment. These agents generally function by forming a layer or crust of material covering burning metal. The idea is to prevent oxygen entering the flaming mass. In order to sustain a fire, 3 conditions must be fulfilled: combustible material, oxidant, and temperature. In this simple experiment, a PC battery is heated up. When it starts to burn, it falls into a measuring cup filled with water. The battery continues to burn for a short while, even after it's submerged. Since batteries contain oxidants, preventing oxygen entering the flaming mass is not an effective way to extinguish a fire. In addition to the Class D metal fire extinguisher, the FFI have tested the effect of several common agents on lithium battery fires. The battery used for demonstration purposes was carefully selected in order to prevent injury to personnel. The batteries are heated up on a hot plate. After a fire has started, the hot plate is removed so that it doesn't influence the test any further. Here, ABC, a dry chemical extinguisher, is used. The extinguisher fails to put out the fire. The situation is exactly the same when using carbon dioxide. Halon also fails. Here, the metal fire extinguisher is used in an attempt to put out the fire. As expected, due to the good cooling effect, only water and water with 3% AFFF were effective. But even with water, the battery reignites. So when using water, use a lot and keep doing so for a long time, but be aware of the risk of fragmentation if the battery is confined in a closed container.
These experiments show that when a lithium battery is exposed to abusive conditions, all cells may not necessarily explode, and there is a delay between each cell explosion. This reduces the overall effect. However, lithium batteries are not harmless. Even a single cell can cause severe damage. Especially when the battery is confined in a closed container, there is a risk of fragmentation. In case of fire, use a large amount of water and, if possible, remove the battery from the heat-affected zone. Luckily, accidents caused by lithium batteries are rare, and the consequences of an abusive condition can be reduced through intelligent battery design and the use of containers that either have a built-in weak point or are strong enough to withstand an explosion.